So in last two classes, we have developed this dichotomizer, and we have seen one example for a dichotomizer with 6 samples, and we have solved, say, 2-class problem. In last class, so what we did was the extension of this 2-class problem into multi-class problem. So question was, can we extend this for many classes? So what is our key idea here is to draw a line so that this becomes one class and this becomes other class. So can we have more classes, or can we classify few more things using similar method? So the thing is, from minimum distance classifier, can I go for k different classes? Instead of 2, can I go for k different classes? So what we need to do is to find out k prototypes. In previous method, x1 and x2, they were found out based on data, so that I can solve a 2-class problem. So what we have to do is, instead of that, now I am doing x1, x2 up to xk, so that I can classify input into k number of classes. So again, we are using the same minimum distance classifier technique, and we are re-deriving what we were doing there. Say this was distance d1, then you can write this distance norm of this vector, difference vector, that is x test and prototype x1. So concept is, you have this xt or test sample, you have this prototype x1, you will find out distance d1. So this d1 is xt minus x1 vector norm of that. So this vector is xt minus x1. So you can say, actually, if I draw properly, if I take this origin and if I join this point, this is my xt, and if I take some x1, another prototype, so if I join with origin, this vector is x1 vector, this x1 vector is xt vector, and the vector which joins these two is xt minus x1. So this xt minus x1 is this vector so when you find out distance, actually you are finding out norm of this particular vector. So the length of this vector is the distance. Similarly, you can find out distance with the second one, third one, and so on up to k. Now what is our principle here? Go with minimum distance. Go with a class who has the minimum distance with given x test. So x test, you have measured d1, d2 up to dk. Whichever is minimum, choose that label. Suppose this is minimum, choose that label for given x test. That is a simple thing. Now instead of doing norm, we go for norm square. So you can see here I am doing squaring of the distance, so that doesn't harm the main thing, but that simplifies my calculation. So instead of square root here, if I square this, then the square root will go, so my calculations are simple. So instead of d1, d2, I am actually calculating d1 square, d2 square, dk square. So we did a small simplification of this by doing this vector multiplication. I got this di square like this. Then for such di squares, I choose minimum. Instead of di, now I am using di square. And the process is choose minimum distance, that is minimum square distance. Now how to implement this actually? So you can rearrange the terms here. So you will see that the first term is fixed one for all g's. So for gi's, you can see that if I write for suppose g1x, then this is equal to xt transpose xt minus twice of x1 transpose xt minus half x1 transpose x1. If I put here 2, what will change? This becomes 2, this becomes 2, this becomes 2. This first term remains same throughout. This is not going to change. From G1 to GK, this will not change. Suppose this is some 100, then this will remain 100. Whatever will be the other calculations in this bracket, this first calculation is remaining same. This is norm square of test sample, and test sample is fixed. Okay, so this won't change for a given test sample. Now, when this part is fixed and this part is variable, I can play with this second part. When distance will be minimum, so whenever this portion is maximum, this difference is going to get minimum. So instead of searching for minimum distance, if I search for maximum of this value, maximum of this portion, if I go with maximum, actually I am going for minimum distance. So we are doing same thing, but still I will throw this calculation, the first part, so that my computations are reduced. Why to calculate this every time when this is fixed? I can throw this. Okay. So what is left, that I am calling it as some discriminant function. So this is my discriminant function. I can write like this. So Gix is a function responsible for class I. So if I put I equal to 1, then the function becomes class 1 function. If I put I equal to 2, it becomes class 2 function, and so on. So how to calculate Gix? So we are in search of discriminant function that will produce maximum response when a test sample comes similar to that class. Okay, for example, I am recognizing digits 0 to 9. So there will be a function g1, say, or g0x for this, then g1x for 1, then g2x for 2, and so on up to g9x. So whenever suppose I fed this system, say number 3, then g3x will produce largest response, maximum. That means its distance is minimum with the prototype. Okay, so there will be a prototype x3 stored in this function. Where it is stored? So when I want g3x, you see that this will be x3 transpose x minus half x3 transpose x3. So to find out g3x, what is required? You require a prototype x3. That's all. So for each class, we require one prototype. So if you are able to find out that, our job is done. Now how do I implement this? You can see here this diagram. This is my input pattern X. Okay, and this is one neuron kind of a thing which is implementing G1X, this neuron is implementing G2X, this neuron is implementing so on like GKX. Okay, so there are so many neurons. How many neurons? There are K neurons. Why? Because I want to learn K classes. Okay. Now if you see, say neuron number 1, this will be responsible for class 1. Now what will be this implementing? This should implement this G1X. What will be G1X? G1X will be Xi transpose X minus half Xi transpose Xi. So I will write here GIX is Xi transpose X minus half Xi transpose Xi. Am I right? You can check here. Xi transpose X minus half Xi transpose Xi. So this I want to implement throughout this diagram. So the first one is G1X. So how I will write? This will be G1X equal to X1 transpose X minus half X1 transpose X1. What will be G2X? Similarly, G2X is X2 transpose X minus half X2 transpose X2 and so on. Okay, so if you see these connections now, this X, which is input pattern, is appearing. Suppose I write here X equal to some X1, X2 up to Xn. So it is n dimensional input. So from this point to this neuron, there are n number of connections. And there is one more terminal, that is n plus 1th terminal. So what I should write here, W11, W12 and so on up to Wn. So there will be one terminal here, W1n. So W1n and up to W11. So if I take this group, this should get multiplied with this input. What will be net here for this neuron? Net at this position is X1 multiplied with W11 plus W12 multiplied with X2 and so on up to W1n Xn plus this extra terminal. So plus Wn plus 1. Okay, so if you compare these two equations, if you substitute here X1, what will happen? So it will look like W1, which is weight of the first neuron. Okay, these are the weights of first neuron. So what should be weights of first neuron and what should be this biasing term so that this G1X is implemented? Now if I put all the weights equal to the prototype value, so if I put W1 vector equal to X1, okay, that means this will be X11, that is prototype 1 and first dimension. This will be X12 up to X1n and so on. And this will be W1 n plus 1. So what it means that the last terminal here should implement minus half x1 transpose x1. So this is the number which will be a thresholding number here. So when you multiply, you will get x1 transpose x, where you will get this. So the first portion of your G1x will be here, and the second portion minus half x1 transpose x1 will be implemented here. So this will be equal to minus half x1 transpose x1, and the first part is equal to x1. Okay. So similarly, this will be x2 prototype placed here directly. So there is no training actually. Once you compute prototype, your training is done. We will take one example so that this will be clear more. This will be x2 transpose x2 multiplied by minus half. Okay, like that we have to just calculate depending on number of k we want. Suppose I take a 3-class problem. If I take a 3-class problem, such kinds of surfaces are generated, and this is my boundary, decision boundary for 3 classes. So this is class 2. G1x is responsible for class 1. G3x is responsible for class 3. So any sample, suppose some sample is over here, then if you find out to which class it belongs, what you do, you find out the intercepts of this point to 3 functions. You will see that this x test will produce largest value at G3x, because this G1x is falling down like this from this point. So this is going down. G2x is also going down. So this portion is going down. This plane is also going down. This point x3, x test will hit x3 here. So this will be maximum value. And what we do? We choose max value and we throw index of that function as our output. So what is output here? Output will be class 3. Now we will take a simple 3-class problem and assume that we have different samples, and based on those samples we have calculated 3 prototypes, because our problem is a 3-class problem. So what I have done, I have calculated centroids for 3 different classes. So in your problem, suppose in exam, this is not given directly. So you are being given, suppose class 1 samples are, some samples are given here. Then class 2, few samples are given here. Class 3, suppose 10 samples are given here. So for class 1, 8 samples, for class 2, 9, and maybe class 3, 10 samples. What you will do? You will take class 1 samples. Okay, then you will find out prototype x1 equal to some samples, say x, suppose class 1 sample, first one, and then x1 2 and so on up to x1 8 divided by 8. So that will give you a mean of that. Similarly, you will calculate x2 from x2 1 up to x2 9 divided by 9. So you take average. Then for x3 you will go x3 1 and so on up to x3 10 here divided by 10. So these 3 prototypes you will calculate like this, and in this problem they are given you directly. Okay, suppose there are 100 samples, and then you will take out sum that and divide by 100. Suppose there are 200, then you will sum all individual coordinates and divide by 200. If there were 400, then you will do. So it's very simple. Suppose these are 3 prototypes already calculated. So these are calculated. If it is not given directly, you have to calculate. Question is, design a classifier to classify input 5, 5. Input is 5, 5. Now where this belongs? So there are 3 options: class 1, class 2, and class 3. Our task is to justify our decision to which class this belongs. Now what is done? First of all, we can plot these prototypes. Prototypes are 10 to 2 minus 5 and minus 5, 5. So you can plot here the prototypes. So prototype 1, that is x1, is here, 10, 2. Then prototype 2 is x2 is here. Prototype 3 is minus 5, 5 is here. Okay. Now suppose this is the sample given to you, X test, and you want to classify. So what is our basic principle? Try to remember that. You find out distances with prototypes. So this will be distance d1 with class 1. This will be distance say d2 with class 2, and this will be distance d3. Okay. So visually I can say distance with d1 is less than d2 and d3. So our decision should be class 1. So visually we can verify this since this is a 2-dimensional case. Now suppose I put here, instead of sample placing here, suppose I put X test here. You will see that this distance d3 and this distance d1, they are same. So d3 is equal to d1. No doubt it is not the distance with d2 or class 2 is more than d1 and d2, but you can check that these two distances are same. So you cannot decide the sample whether it belongs to d3 or class 3 or class 1. So you will find that throughout this line you cannot really decide to which class it belongs. Or in other words, if I join these two prototypes and take the center point and draw a perpendicular line, that is the decision boundary between class 1 and class 3. Okay, so this side is class 3 and this side is class 1. Center value or center position will give you the decision boundary. Similarly, if I join point 3 and point 2 and take the center point, draw perpendicular, then this will be the decision boundary between class 2 and class 3. So this side will be class 1 and class 2. You can join this P2 and P1 like this, draw perpendicular. So this will be the surface S12, this is surface S13, and this is surface 23. So you can see in previous diagram, this will be the situation in 3 dimensions. So these are the boundaries, actual boundaries. So I can call this boundary between class 2 and 3 as S23. This will be S12 and this will be S13. Okay. So if you see from top, these are the boundaries. So if you see from top, you can see like this. Now what is expected is any sample which is in this shaded region, so any sample in this shaded region belongs to class 1. Okay. Any sample in this shaded region belongs to class 2. You can see it is covering prototype 2. So domain, or the, you can say, region of class 2 is confined by this boundary. So whatever may be sample lying over here belongs to class 2. Whatever may be sample lying, whichever may be sample lying here is class 3, and whichever may be sample you choose in this region belongs to class 1. So I hope you can imagine that planes on this diagram. Now take our equation that is already derived for this problem. We have GIX. So this is our discriminant function based on minimum distance principle. So I know that this is Wi transpose X plus Wi n plus 1 for I equal to 1 to R. R here is equal to 3. And what is Wi? Wi is straightway equal to Xi, that is your prototype. And Wi n plus 1, this component is minus half Xi transpose Xi. Now you can see here, I am designing now G1X. How it is designed? I take the prototype, that is 10-2. X1 is, I know it is 10-2, which is calculated, or in this problem it is given to you. It belongs to class 1. So since I am designing G1X, I will take the prototype which belongs to class 1. So this 10-2, it is W1 transpose X. I need to calculate this. So X is two variables, X1 and X2. These are space variables. Then plus minus half into Xi transpose Xi. So this is X1 transpose multiplied with X1. So if you simplify this, you will get 10x1. So this 10 gets multiplied here. 10x1 plus 2x2 minus 52. Then we will go for G2x. So this is x2 transpose x plus minus half x2 transpose x2. Okay, and x2, remember, it was 2 minus 5 for class number 2, and since we are designing G2, I will take this x2. Now if you multiply this, G2x is 2x1 minus 5x2 minus 14.5. Then we go for third function, discriminant function. Then I'm going to use x3 transpose x and minus half x3 transpose x3. So x3 here is minus 5, 5. So just multiply this. You will get minus 5x1 plus 5x2 minus 25. Okay. Now I have three different equations ready for me. This is equation 1, 2, and 3 for three classes. Now how do I implement this? You just see this equation number 1 and is implemented by this neuron number 1. So what I am doing now, take this 10 and 2, just place here, where for x1 terminal you just write its coefficient, that is 10. For x2 terminal, write its coefficient 2, and for third terminal you write that 52, minus 52. And for that terminal you connect this terminal to +1. So this is a fixed connection. This won't change. These two are variables. Depending on your input, only these two terminals will vary. This third one is fixed. Now what is implemented here? If you remember, net value here is 10 into x1 plus 2 into x2 minus this 52 into 1. So this is this. So what is this? This is nothing but our G1x. Similarly, this neuron number 2, it will take coefficient 2 and -5. I am writing here for x1 and x2 respectively. I will add one extra terminal with fixed connection to +1, and that has a multiplying factor or weight which is -14.5. So that is placed here. So what is implemented here is equation number 2, which is nothing but G2x. Then I will take third neuron. Why I am taking 3 neurons? Because my problem was class 3 problem. That is, number of classes were equal to 3. Now G3, you take this -5 plus 5. So -5 plus 5 and -25. Now our design is complete. Okay. So the final circuit will look like this. This will be our neuron number 1. This will be our neuron number 2. This will be our neuron number 3. They are implementing G1x, G2x, G3x. Just see same thing that we have designed. Now next to that is a max selector. So whichever function produces maximum value, its index is thrown as the output. So there are 3 options, 1, 2 or 3. Now our problem was we were given x test equal to 5, 5. And question was classify this. So what we have to do? We have to take G1x. So if you take this diagram, then our x test was 5, 5. So I have to place here 5, x1 equal to 5, x2 equal to 5. So this will be common to all. Okay. So all equations will receive same input, and for the same input, we will calculate respective values of G1x, G2x, G3x. So substitute here 5, 5, then 5, 5, 5, 5. Okay. So you can write like this, and then you will get G1x equal to 8, G2x equal to -29.5, G3x is equal to -25. So max of 8, -29.5 and -25 is 8 obviously. So index of that function. The index of that function is what? So 8 is produced by G1x, index of that is 1. So my answer is input x test equal to 5, 5 belongs to class 1. Okay, so this should be my answer. And the surfaces are like this. So 5, 5 somewhere here, say this is minus. Okay, so this is somewhere here is 5, 5. Backside of this plane. This is your x2 axis, this is your x1 axis, and the third dimension, you can see here it is written G1x, G2x, G3x. So 5, 5 is somewhere backside, so it is hitting somewhere here at position 8 for G1x. For other functions, this is hitting, say, this G3 is going like this, and G2 is going like this. If I extend these planes, it will look like this, and they are hitting this 5 5 in negative zone. Okay, so that's why G1 is producing largest output, and I will declare that as my uh, class for given input. So if you see the diagram here, the space x1 x2 space is divided into three subspaces. Okay, some three spaces, say like this, something like this, and this is one zone, this is another zone, this is another zone. So we are dealing with three classes. Suppose there are 10 such classes, then we have to design such 10 G1 function, say G1 to G10x functions. Okay, and we can solve such problem. Note that these are linearly separable classes. So what we are dealing with is a typical case, may not be practically useful. Theoretically, it's fine. If the problems are very simple, then you can play with those problems using these simple techniques. You may not go even for say big circuits. You can go with this. So a good researcher or good designer will start with a small circuit. It will check, or he or she will check whether given problem can be solved with small architecture. If not, then one should go with higher architectures. One cannot go directly to deep learning layers and solve such kind of problems. Okay, that is not required. So that will be wastage of resources. If I can do with one neuron, why should I go with 100 or 1000 neurons? Okay. So keep this thing in mind. So next thing we will see in Monday's class. If you have any doubt, you can ask.